Okay, let's do this problem now. So again, with the triple integrals, really, I think the most difficult part is trying to figure out what the region is. So the way that I've given this to you, let E be the region under this plane, z is equal to 1 plus x plus y, and above the region in the xy plane bounded by these curves. So really, since the way that this is given, this tells you that the z integral needs to be on the inside and the x and y integral needs to be on the outside. That's what this is saying. The floor is going to be some region in the xy plane, and the ceiling is going to be this z is equal to 1 plus x plus y. Okay, so if you were to graph this region in the xy plane, or graph the projection of this region onto the xy plane, you get something like this. So this is the x, this is the y. Okay, so y is equal to the square root of x. Let me switch to red. Y is equal to the square root of x is going to be this. Y equals 0 is going to be this. And then x equals 1 is going to be this. And so the region that we care about is the region that's enclosed in this area right here. Okay, so this is like the base of the shape that we're integrating over. Okay, it's the base of the shape that we're integrating over. The floor is the xy plane, and the ceiling is going to be this plane here. So then the z integral for every fixed x and y value in this region here, for every fixed x and y value, z is going to go from 0 up to 1 plus x plus y. So the z integral, this is going to be z equals 0 to 1 plus x plus y. Okay, now we do the x and y integral. So you could either integrate with respect to x first or with respect to y first. I'm going to do y first. So this says for every fixed value of x, we're going to integrate from y equals 0 up to this parabola, which is y is equal to the square root of x. Okay. So now y will go from 0 to the square root of x. And then x, the x integral is going to go, the x range is going to go from 0 to 1. Remember, this vertical line here is x equals 1. Okay, so now this is going to be the integral from x equals, that's x equals 0. That's a strange mistake to make. X equals 0 to 1 to xy and then dz dy dx. And this is 65 over 84. Again, this is just an iterated integral. The new thing about this problem is not that there's 3 integrals, it's that the region we're integrating over is in 3 space. That is the novel thing, the difficult thing that you have to wrap your mind around. So let me try this again. This is 65 over 84, and now the integral just amounts to doing an integral of 3 different polynomials. So it's tedious, but it's straightforward. Okay, now we are on to this problem. Okay, so now here are it's enclosed by the surfaces z is equal to x squared minus 1, z is equal to 1 minus x squared. Now this z is equal to x squared minus 1, the way this looks like, this is like a parabolic cylinder or something along those lines that is going along the y-axis. And same thing for this. So take some time and put these in GeoGebra and see what these surfaces look like. So in this problem, really, the floor should be y is equal to 0, and the ceiling should be y is equal to 2. Okay, of course, in this case, the floor and center are the floor and ceiling are oriented, left to right rather than up and down, but those are just kind of the things that I like to call them. So if you look what this region looks like in the xz plane. Notice I'm saying xz, not xy. That's not a typo. Okay, so if this is the x-axis and this is the z-axis, so this region, z is equal to x squared minus 1, well, this is going to be an upward-facing parabola that looks like this, and the region z is equal to 1 minus x squared. Well, notice that these two are going to be equal when x is equal to plus or minus 1. So this is z is equal to, let me just write this here, this is z is equal to x squared minus 1. Okay, and 1 minus x squared is going to be an upside down or a downward facing parabola that crosses the z-axis at positive 1. And so this is going to be z is equal to 1 minus x squared. Okay, now the y integral is going to be on the inside, okay, because y is going to go from 0 to 2. So we have this region. The region bounded by this surface is z equals x squared minus 1 and z equals 1 minus x squared. These are going to look like two cylinders, but instead of being like circular cylinders, they're parabolic cylinders, and it's going to be centered on the y-axis. Okay, and the plane y equals 0 and y equals 2 just takes this section of that parabolic cylinder going from y equals 0 to y equals 2. Like I said, graph this in GeoGebra. So this tells us that for any fixed value of x and y, or sorry, x and z in the xz plane, y is going to go from 0 to 2. So in this problem, the y is the y-axis that is coming out of the screen. So this is going to be y equals 0 to 2. Okay, now we need to figure out the bounds in the xz plane. Okay, so we'll integrate with respect to z first. So for every fixed value of x, we're going to go between these two parabolas. So we're going to go from z is equal to x squared minus 1 up to z is equal to 1 minus x squared. So this will be z equals x squared minus 1 to z is equal to 1 minus x squared. This is 1 minus x squared. And then lastly, the x integral. The x integrals are going to go from this point to this point, but we already saw that the place where these two parabolas intersect is when x is equal to plus or minus 1. So now x is going to go from minus 1, x is going to go from minus 1 to 1. Okay, we'll put in the dy, dz, dx, and the function that we're integrating is x minus y. And when you evaluate this, you see that this is equal to minus 16 over 3. And again, this is a straightforward integral to do. It's going to be essentially integrate 3 polynomials. There'll be a polynomial when you do the y integral, then one when you do the z integral, then one when you do the x integral. It's tedious, but it's straightforward.